probably hand out one other problem set after that. So I'll probably hand out a problem set 9 this week, which will be next week. And then I'll probably hand out one more problem set, which will be the final problem set in lieu of a final exam for the class. But it'll just be a normal problem set, except it'll be more fun. Good. Okay, so today I want to discuss a sort of exciting topic, a very important topic, and one which is a bit of a shift from things that we've considered so far in this course. So maybe I could just set a minute and set the stage for what we've done and where we're going. So having finished with our discussion of Yang-Mills theory, we've spent some time thinking about the role of continuous symmetries in quantum field theory. In particular, we saw that you can have global symmetries, which give you conserved currents and help you organize the states in the theory. And you can also have gauge symmetries, where you promote those global symmetries to local symmetries, and then you get some new dynamics associated with that. And indeed, as you learned last week, for the last several weeks, these gauge symmetries are important in describing all sorts of fundamental interactions, including the strong nuclear force, as you saw one guy taught you about, QCD. But so far, we've talked about symmetries, but we haven't talked about what I think is one of the most important things, which is how these symmetries help you organize your thinking about quantum field theory, even if the symmetries disappear. Okay. So in particular, what I'm going to start talking about today is the subject of symmetry breaking. In particular, I'll talk about what's known as spontaneous symmetry breaking. This is an incredibly important subject. It really helps us organize our way of thinking about quantum field theory and its applications not just to particle physics, but condensed matter physics. And it'll be leading us in next class to the sort of grand unification of the theory of symmetry breaking with Yang-Mills theory, which will lead us to the Higgs mechanism and to the electroweak theory. And before next week, we'll sort of end the course with a bit of a summary of the standard model of particle physics and some of its features, really based on our previous discussion of Yang-Mills theory and our discussion this week of the Higgs mechanism. Okay. So before getting into any details of spontaneous symmetry breaking, let me just consider a very simple example. Okay. I'll consider a theory that we've considered many times before in this class, which is phi-4 theory. Okay. So as usual, the Lagrangian has a kinetic term along with an interaction term, which is given by a potential that is quadratic and has a quartic interaction. Okay. And I guess if I want to be super precise here, I would put my factors of 1/2 and 1/4 factorial here. And what does this potential look like? So if we were to study the classical dynamics of a scalar field, then, for example, the constant mode of the scalar field would just be described by a particle rolling around in a potential. And the potential v of phi would sort of look like this. Okay. It has a minimum at phi equals to 0, and it increases quadratic, or to like phi to the 4th as phi becomes large. Okay. And one interesting feature about this theory is that it has a symmetry where phi goes to minus phi. So, for example, that symmetry forbids the existence of a one-point function. So you know that if you started computing loop corrections and stuff like that, all of the tadpole diagrams like this that would give you a one-point function for phi would have to cancel, because any term linear in phi in the effective action would not respect this phi goes to minus phi symmetry. Okay. So what does that mean, the phi goes to minus phi symmetry? Well, it means that if you were to study the Hilbert space of this theory, there is an operator, I guess we could call it Z, that implements this phi goes to minus phi symmetry, so that, for example, if you conjugate phi by Z, it'll take phi to minus phi. Okay. So remember, phi is an observable. And the unitary operator z that implements the symmetry acts on observables by conjugating them. Okay, you take z inverse observable z. Okay. And so z is a unitary operator. And because it takes phi to minus phi, it squares to 1. So, in fact, one can also show, and this is an easy exercise, you should prove it to yourselves, that any unitary operator that squares to 1 is also a Hermitian operator. Okay. So z is both a unitary and Hermitian operator. And the presence of this symmetry will lead to all sorts of interesting consequences. It will lead to selection rules. It leads, for example, to all sorts of constraints on endpoint functions. But what I'd really like to do is consider a slightly different theory with the z goes to minus z symmetry. What I'd like to do is consider the case where the parameter m squared that has been appearing at the potential is not positive, but rather negative. You know, I've been calling it m squared so far because, well, m would be the physical mass of an excitation around this phi equals 0 vacuum state. But it's just some parameter in the potential, and so there's no reason why it couldn't be negative. And if it's negative, well, then that means that the potential looks something like this. In particular, the point phi equals 0 is now unstable. And you will have two stable minima at some values of phi that I will call minus v and plus v. Okay. So in particular, if we could rewrite the potential now, so that's, you know, 1/2 m squared phi squared plus lambda over 4 factorial phi to the 4th, where m squared is negative. It's then completely straightforward to rewrite that. So I just will rewrite it for you. I won't bother to work out the algebra, but you can rewrite this as 1 as lambda times phi squared minus v squared quantity squared plus a correction term. That's just some constant. So we do that just by completing the squares. And the quantity that I've called v is the square root of 6 times, well, the absolute value of m squared now, because that's a negative number, over lambda. Okay. So what does this mean? This means that if you were to study the phi equals 0 state, what we'd been previously regarding as the vacuum state or the ground state of the theory, that state will be unstable. And the scalar field will like to roll down the potential and arrive at one of these two global minima where phi is equal to plus or minus v. So there are now two classical minima of the energy where phi is equal to plus or minus v. So now let's imagine what would happen when we quantize this theory. So when we quantize the theory, what we expect is that we will get not one vacuum state, but two possible vacuum states. That I'll call a state plus and a state minus. And these should have the property that the expectation value of the operator phi in the plus state should be plus v, and the expectation value in the minus state should be minus v. Okay. And moreover, this theory still has a Z2 symmetry. The action is still invariant under phi goes to minus phi. But this unitary operator Z will now interchange these two vacuum states. Any questions on this so far? So this is probably pretty familiar to you from the case of quantum mechanics. So in the case of quantum mechanics, actually something slightly different happens. So it's probably worth comparing the present situation to the situation in quantum mechanics. So if phi were just a single degree of freedom, so the location of a particle, and v of phi were some physical potential, then you would have still a single ground state of the theory. Well, let me say it a different way. If we were studying normal quantum mechanics, then you would organize your states into symmetric and anti-symmetric states under the symmetry where phi goes to minus phi. And that would be a sensible thing to do because in ordinary quantum mechanics, the two states that you would write down, plus and minus, would have non-trivial overlap. You know, the state where it's not the case that there's a state where x is, or phi would be completely concentrated around one vacuum state or the other vacuum state. Rather, you would organize in terms of symmetric and anti-symmetric linear combinations, and the ground state would be the symmetric state between the two. And in particular, if you tried to put the scalar field in one of the vacua, say phi is equal to x, you would find that there's some non-trivial quantum mechanical amplitude to tunnel to the other vacuum. And so, for example, if you guys remember the WKB approximation, in the WKB approximation, this would be the exponential of the integral of the square root of v. Okay, you guys remember that? This is how you calculate tunneling amplitudes in quantum mechanics. And so this would be something non-zero. Okay, you could go ahead and compute it from this expression up here if you like. It would go like the square root of lambda times, I guess, v cubed, because you would get a v squared from here, and you have to integrate d phi from minus v to v. Okay. Now, the difference in quantum field theory is that quantum field theory is like a quantum mechanical system where you have an infinite number of degrees of freedom, and each mode, each momentum mode, would now have to tunnel from the plus vacuum to the minus vacuum. So you get a plus vacuum and a minus vacuum for each momentum mode, and you would get one of these very small exponential factors for each one of those modes, and if you took the product to compute the overlap between these states, you would actually get 0. Okay? So that means that in quantum mechanics, if this were a single potential, there would be some finite amplitude for you to tunnel through the barrier from one side to the other. But in quantum field theory, that amplitude will be 0. Now, actually, there is a whole interesting study in quantum field theory of tunneling processes. So, for example, if you wanted to change the potential slightly, say to make this potential well slightly deeper than this potential well, so that one of those is a true vacuum and the other is only a false vacuum, then you could use quantum field theory to study that tunneling process. It's very interesting. It's a rich subject in its own right, known as the theory of instantons and tunneling in quantum mechanics. But in the present case, we'll just keep the Z2 symmetry preserved so that there won't be any such tunneling. Okay. So let's say that we want to study the vacuum state where phi is equal to v. Okay. So let's say we want to study the theory in the state plus. Well, what would you do? Well, one thing you could do is you could define a new field which is phi minus v, so that your vacuum state is now the state rho equals 0. So all I've done is I've shifted my field phi in order to remove this one-point function. And then you could go ahead and write the Lagrangian in terms of rho. So the kinetic term won't change because all I've done is shift rho, shift phi to get rho. And then it's straightforward to work it out. I mean, I won't bother to bore you with the details. But you get a term of order rho squared, a term of order rho cubed, and a term of order rho to the fourth. So all I've done here is rewrite the action in terms of rho instead of v. And you could see that expanded around phi is equal to v, this looks like some other somewhat random phi-4 theory. Okay, except I've changed the name of my field from phi to rho. But it's a theory with very special values of the couplings. In particular, if I just regarded this theory as some random phi-4 theory, I would expect the coefficient of rho squared, rho cubed, and rho to the fourth to be unrelated. They would just be free parameters. But here you can see that there's one non-trivial constraint among those three parameters, because we have two variables, lambda and v, for those three variables. And that reflects the fact that the theory still has phi to minus phi symmetry. But in terms of this new variable rho, it takes a slightly different form. Rho gets shifted to, what is it, 2v minus rho when phi goes to minus phi. Did I get that right? Something like that. Okay. So what do we have here? We have a situation where the theory still has a Z2 symmetry, but the ground state of the theory does not. And this is referred to as a spontaneously broken symmetry. It's a symmetry where the theory has the symmetry, the Lagrangian has the symmetry, the dynamics has the symmetry, the equations of motion will be invariant, but the ground state does not. And from the point of view of this ground state, the symmetry appears to be nonlinearly realized. So what do I mean by that? Well, in terms of my original theory, when the mass squared was positive, the symmetry took phi to minus phi. So phi went to some linear operator times phi. It was multiplied by a constant in this case. Rho, however, does not get mapped to something times rho, but something times rho plus a constant. So very example, so in this case we say that the symmetry is still present in the theory, but it's not linearly realized. Okay. Now, I should comment on the use of the word spontaneously broken. So we could also just talk about a broken symmetry. That's where you have a symmetry, but then say you add a term to the action which no longer respects that symmetry. So for example, if I started out with my phi to the 4 theory, where I had a phi to minus phi symmetry, if I had a very small cubic term of order phi cubed, then that symmetry would be broken. And if that coefficient of the phi cubed term were very, very small, I could still try and organize my states in terms of that symmetry and expand in powers of that coupling constant. This is a different situation we're talking about here, where the symmetry is spontaneously broken in the sense that the symmetry is still present in the theory, but the ground state of the theory is not actually invariant under that symmetry. And as we'll see, this is a situation that occurs all over the time in physics. So for example, in materials physics and condensed matter physics, there are all sorts of cases where this occurs. And what we'll do here is we'll introduce some very general property of systems with spontaneously broken symmetry and see that a lot of physics that you know about already can be organized by thinking about it in terms of these broken symmetries. Before I continue, let me pause and see if there are any questions. So one question you might have is that I claimed that the theory still has this phi goes to minus phi symmetry, this unitary operator Z, even at the quantum mechanical level. And this is usually the case. So it is usually the case, or I should say it is often the case, that a classical symmetry, that is to say a symmetry of the classical equations of motion, is preserved in the quantum theory. But that's not always the case, because sometimes there are anomalies, which I believe you learned a little bit about last week. And in the case where you have anomalies, then all bets are off. Okay. So we will, hopefully by the end of class today, meet one case of a spontaneously broken symmetry which is anomalous. Okay. And then we won't be able to derive anything too useful from that. But typically, usually it's the case that a classical symmetry is preserved in the quantum mechanical theory. And the point is that these anomalies arise. Well, there's a bunch of different ways of thinking about anomalies. But one interesting way that you can think about them is by thinking about the path integral formulation of quantum mechanics, or quantum field theory. Remember, a classical symmetry is an invariance of the Lagrangian. But when you compute things like scattering amplitudes, you have to integrate this Lagrangian over some fields, some quantum fields. And so you have two sort of ingredients in a path integral. You have the classical action, which is invariant, and you have the measure factor, the integral d phi in your quantum field theory measure. And anomalies can be thought of as arising when the path integral measure d phi is not invariant. In the present case, however, we're talking about a phi to minus phi symmetry. And so it's almost obvious, it's kind of obvious, that that thing should be invariant under phi goes to minus phi. Okay. So for example, if you imagine integrating over field variables phi, then you could also write that as an integral over the field variables minus phi. Okay. And nothing too fancy should happen. The anomalies that you met last week can be regarded actually reasonably precisely in terms of a failure of the path integral measure to be invariant under the symmetries that you're thinking about. That's not something that I'll try and push explicitly, but I just wanted to bring this up because in the present case, where you have a phi goes to minus phi symmetry, this is not anomalous. And that means that it's respected in the quantum theory. So what does that mean in particular? Well, for example, let's stare at this action that I wrote down up here for rho. You could imagine computing all sorts of quantum corrections to it, counter terms, so on and so forth. And I told you that this phi to minus phi symmetry implied a special relationship between these three coefficients. And if the phi to minus phi symmetry is preserved, then that special relationship has to persist at all orders in perturbation theory. Okay. So, for example, it would be a reasonably straightforward exercise to go ahead and start computing counterterms in this theory and checking that they all obey the right sort of relationship, order by order in your coupling constant, to ensure that this Z2 symmetry, that this phi to minus phi symmetry is preserved. We could go ahead and do that, but that's sort of aside from the main thrust of what I wanted to discuss today, so I'll just sort of leave that for an exercise. Oh, maybe that would be a good problem. Okay. Any questions before I continue? So this was a very simple example, but I just wanted to introduce it so that I could introduce the language of spontaneously broken symmetry before discussing a somewhat more complicated and more interesting case. Yes?
Why would you pay particular attention to the ground state and its symmetries? Because it usually has all the symmetries of the theory.
Well, it is certainly not the case that ground states usually have all of the symmetries of the theory. You know, the theory of that describes the dynamics of this room is translationally invariant, but the state of this room is not. It would be sort of boring if it was. So it is. You know, it happens all the time that you're studying a theory. So whenever you study a theory in a state that does not respect all of the symmetries, then you could. That's essentially a spontaneously broken symmetry. Well, we use the phrase spontaneously broken to describe the ground state. Yeah. I mean, one can also, even in theories where you have, if you want to study some excited state that breaks the symmetries, you could also use the symmetry in that case. But I'm going to talk, you know, the consequences that I'll describe today involve the case where the ground state breaks the symmetry. I mean, if you want an example, like here's a great example. I mean, a great example, a sort of more sophisticated example of spontaneously broken symmetry. I mean, they appear all over the place. But here's an example. Okay, let's take a magnet. Okay, what is a magnet? A magnet, in a simple model, is a bunch of spins. Okay. And as you probably know, if you take sort of a standard ferromagnet, there are, you know, two kinds of phases. There's an ordered phase and a disordered phase. If you study the theory at high temperature, then all of the little spins that make up the magnet are not aligned with one another. And averaged over long distances, the system is rotationally invariant. There's no special direction. However, if you lower the temperature of the magnet, then the interactions of these little spins will make them want to align. And so the ground state of the theory will be a system where all the spins are aligned. But suddenly, that means that ground state has picked out a special direction. It's spontaneously broken the rotational invariance of space, and the ground state of the theory now has broken some of the symmetries. So it's you know. Okay, and indeed, I want you to think of this model of a magnet as we continue with our discussion, because that is, I mean, essentially the system that we'll be studying. It's slightly different I mean, you could think of the magnet, of course, as a field theory, where instead of describing a discrete vector at each point on a lattice site, you imagine averaging in some way, studying at distances long compared to the lattice site. Then you would have a sort of vector at each point in space. And indeed, you know, dependent at low temperature, the statement would be that the rotational symmetry of the magnet is spontaneously broken. Whereas at high temperatures, the rotational symmetry would be preserved. And indeed, if you study, this is a little off topic, but if you study the free energy of a magnet as you go through this phase transition, it's literally the case that the free energy looks like this at high temperature, and the free energy looks like this at low temperature, where phi is now some field describing the magnetization. Yes?
You want to continue on?
No, ask your questions.
So maybe a stupid question, but if it happens that our ground state is equivalent to some other state or system through some symmetry, for example, I'm thinking about conformal symmetry.
Yeah.
And then the spontaneous breaking the ground state is equivalent to the spontaneous breaking a high energy state or something like that. Or for example, if we have gate symmetry, some state is related to some other state.
Yeah, we're going to get to a a lot of these things. So, okay, we have to first crawl before we fly, and then we have to walk and then run and build an airplane and then fly. Okay. Yes. Okay. So right now I'm talking about this very simple symmetry. But as I think both of you have sort of anticipated, what I want to do is consider the case where I don't have a discrete symmetry, but rather a continuous symmetry. So in the case of a magnet, it was the rotational symmetry, which is a continuous symmetry that gets spontaneously broken. So, for example, let's just take the theory of a complex scalar field. So again, I'll call it phi. And, okay. So I'll be a little relaxed about all of my numerical factors everywhere. So if m squared were positive, then this would be a standard scalar field with a complex scalar field that has some charge associated with the U1 rotational symmetry, the U1 phase rotation of the scalar field, where phi goes to e to the I alpha times phi. So that's a continuous global symmetry. But the point now is that if we take the case where m squared is less than 0, then what does the potential look like? Well, it's a little hard to draw because it's, yeah, okay, I'm not going to try and draw it. You know, it's sort of, it's sort of, people sometimes call it the Mexican hat potential. You know, so it sort of looks like that. If you sort of see what I mean. Do you see what I mean? You kind of see what I mean. Okay. That's supposed to be v as a function of phi and phi bar. So if m squared is equal to 0, what does the solution look like? Well, the solution will be equal to v times e to the I theta. So here, let me just be a little bit more specific. So here v, again, if you just work through the algebra, is some parameter that goes like the square root of m squared over lambda. And so the classical solutions to the equations of motion will just say that phi is some complex number whose length is set by the value of the couplings lambda and minus m squared in the theory. And so we now have a one-parameter family of vacuum states labeled by theta, which is the phase of phi in the vacuum. So when we quantize the theory, we actually expect to have to make a one-parameter choice of what the vacuum state of the theory is. And, of course, this vacuum state is defined by the statement that the expectation value of phi in the vacuum is v times e to the I theta. And that 1 over root 2, I guess that's just a convention. When we come back and study the Higgs mechanism, we'll return to all of these equations. Any questions on this so far? Now here's the interesting thing. This theory has a shift symmetry. So the rotational symmetry of phi has become a shift symmetry of the parameter theta. So what does that mean? That means that you could imagine changing theta without changing the energy at all. So theta is some scalar quantity which you could change without changing the energy. And indeed, you could imagine a fluctuation of theta that has some dependence on space. And if the dependence were just constant in space, it would have zero energy. So it's a fluctuation of the system that is dependent on space, and at very long wavelengths it has zero energy. We have a name for such a thing. It's a massless field. So this means that when we study the theory, expand it around this vacuum, there should be some sort of massless scalar field. So let's understand that explicitly. So explicitly, what we want to do is we want to take phi and we want to expand it around this vacuum state that we chose. So the vacuum state was 1 over the square root of 2 times v times e to the I theta. And what I want to do, so what I'll do is I'll just say allow this radial coordinate, the absolute value of x to fluctuate, and I'll call its fluctuation rho. And I'll allow the phase to fluctuate, and I'll call its fluctuation chi. And then it's straightforward to go ahead and rewrite our Lagrangian. So our Lagrangian up here, I wrote it down for you, in terms of these fields, rho and chi. And what does the dynamics look like? Well, you'll get some dynamics for rho. Rho will be some massive scalar field whose action is actually going to be essentially identical to the action here that we wrote for rho. But the important point, so you'll get some kinetic term for rho, just like this. But you'll also get a kinetic term for chi. So let me just write this down for you. Rho over v squared times d mu chi, plus a bunch of other interaction terms. So you'll get an m squared rho squared term, and then you'll get a bunch of other rho interactions. You'll get a rho cubed term and a rho to the 4th term. But the point is that chi is a massless scalar field. Now it still has non-trivial interactions, right? So it interacts with this rho field. But the point is that chi must be massless because of the shift symmetry where theta goes to theta plus alpha, or chi goes to chi plus alpha. And it's impossible to write down a mass term that so that a mass term for chi would break the chi to goes to chi plus constant symmetry. And this is an incredibly powerful and interesting result, which is known as Goldstone's theorem. And it says that for every spontaneously broken symmetry, that is to say, for every spontaneously broken continuous symmetry, we have a massless scalar field. And this scalar field is known as a Goldstone boson, or sometimes as a Nambu-Goldstone boson. And there's one for every broken symmetry. And again, by broken symmetry here, I mean a spontaneously broken symmetry. So that there is one scalar for every symmetry of the Lagrangian, or symmetry of the dynamics or the equations of motion, that is absent in the vacuum state. Questions? Yes.
Why theta is constant?
Well, theta is constant just because I was looking for the lowest energy solution of the theory.
But the crystal,
Right.
crystal could depend on space time.
Well, I'm looking for the vacuum state of the theory. And a vacuum state is supposed to be a state with as low energy as possible. That's what we mean by vacuum. And so if I made theta a function of x, then you would raise the energy of the state. So now, of course, there are solutions where the phase has a function of x, but they're not vacuum solutions. So the ways that I'm choosing to write the theory is I'm saying take phi to be, a constant, because that's going to be the lowest energy solution, and then study the excitations around that. Those will be the low energy excitations of the theory. And what we see is that when you have a symmetry of the action that's absent in the ground state, then necessarily you get a massless degree of freedom. To some extent, there's some truth to the statement that every massless degree of I should be careful. There's some extent. So to some extent, almost all of the massless scalar degrees of freedom that you have ever heard of are Goldstone bosons. And we'll encounter a few of them. Okay. Any other questions? Yes.
Is it applicable if we put the system in a box? Well, once we put it in the box, we break the symmetry of the Lagrangian.
I mean, yes. So if you break the symmetry of the Lagrangian, then you don't have a Goldstone boson.
No, but the Lagrangian by itself is has a symmetry. Let's say
Yes.
we take any
Well,
Lagrangian.
Certainly if you put the theory at finite volume, but you don't have a symmetry, but you preserve the symmetry, then you'll have a Goldstone boson.
Well, some of the symmetries got broken once we put the system in the box.
So I guess are you breaking, what symmetry are you breaking?
Let's say the Lagrangian has a rotational symmetry and translational symmetry.
If
Once
you-
we put it in the box, we break both.
Then you won't have a Goldstone boson.
Okay.
But of course, if the box is very large, then translation symmetry is almost true, and you will almost have a Goldstone boson. Does anyone know the name of a Goldstone boson associated with broken translation? Yes. Okay. Or, well, I guess, here, let me be a little bit more explicit. So let me give you some examples. So let's take our example of a magnet. So in the case of a magnet, in the magnetized phase, where your ground state has suddenly chosen a direction, the Goldstone boson, what is it? It's a small fluctuation in the direction that the magnets choose. So the Goldstone boson is known, well, as a magnon. And what is it? It's a small fluctuation in the magnetization. So in particular, you imagine being in the ground state where all of your spins are aligned, and then you imagine perturbing them in some region. That perturbation will propagate, and it'll propagate like a massless degree of freedom. How about another example? Let's imagine that we have some sort of fluid. The dynamics of the fluid, whatever they are, I mean, this is not a class on fluid dynamics, but the dynamics of the fluid, whatever they are, better be invariant under boost invariance and translation invariance and rotation invariance and all of that stuff. In particular, what is boost invariance? Boost invariance is the invariance that says if you take x and you shift it to x plus vt, where v is some constant, then the dynamics is the same. So this is Galilean boost invariance, or in a theory of special relativity, you would talk about Lorentz boost invariance. But it's an invariance that's broken if you choose a rest frame. And so in a fluid, you know, the ground state of a fluid picks out a rest frame and so there will be a Goldstone boson associated with that. What is that Goldstone boson? It's a sound wave, otherwise known as a phonon, which is a fluctuation in the velocity of the fluid. Also, if you have some atomic lattice that breaks translation symmetry down to some discrete symmetry, you'll have phonons associated with that. Yes, question?
Why are magnons not vectors? Because they can wave like this, or they can wave like this.
Well, it depends on exactly. So, indeed, you can talk about different polarizations of the magnons, and that depends on exactly what sort of spin system you have. Like if the spins have a preferred lattice, have a preferred direction or preferred plane, or if they're isotropic in three-dimensional space. In the language of the ON model, which we introduced earlier, it depends on whether it's in the phi to the 4 universality class or the O2 or O3 universality class. Okay. Any other symmetries anyone wants to break? Let's see. So this happens all the time in condensed matter physics or in materials physics. So in condensed matter physics, we often have phase transition. And the way that these phase transitions proceed is that you have an order parameter say O has two phases. Well, let's not call it O. Should we call it O? Let's call it M. That's a good name for an order parameter. You have some order parameter M, which is 0 in one phase and non-zero in another phase, with some phase boundary separating them. And if M equals 0, so if M transforms under some symmetry, that symmetry will be broken in the phase where the vacuum expectation value of M is non-zero. And then in that phase, we will have Goldstone bosons. And what are those Goldstone bosons? Well, they are local fluctuations of the order parameter. So the case of a magnetization is great to keep in mind here because there, what is the order parameter? Well, it's the magnetization vector. So if you have sort of an isotropic magnet, then that's just a number. It's 0 in the disordered phase and non-zero in the ordered phase. But if you think about it in the language of field theory, it's a local variable that can fluctuate. And in the magnetized phase, where its expectation value is non-zero, you have these magnon states, where the direction that the magnetization spin can fluctuate, and that will propagate just like a massless degree of freedom. So, for example, if you wanted to study the thermodynamics in this magnetized phase, you would have to include these magnons if you wanted to study the thermodynamics at very low energy, because at very low energy, it's only the light degrees of freedom or the massless degrees of freedom that appear. Questions? I mean, this is an incredibly deep physical principle. No questions? Yeah, no, yes.
Maybe. Are there Goldstone bosons associated with broken time translation symmetry?
Good. So typically, ground states of systems are assumed to be time translation invariant, which means that they would preserve time translation symmetry. There has been some work on so-called time crystals. So what is a crystal? A crystal is something whose ground state breaks translation invariance. It's a lattice rather than having a continuous symmetry. And so there is some work on theories whose ground state has broken time translation symmetry. I haven't read these papers, so you could read those papers and tell me. They look sort of interesting. Yeah. Question?
And Goldstone bosons pick up the mass? Or we'll get to that?
We'll get to that. Okay. So, for example, if the symmetry that you broke is only approximate, then these Goldstone bosons will acquire a mass. So, indeed, if you find yourself, I mean, one of the important things to keep in mind is that very often nobody tells you what the symmetries are, okay? If you find yourself living in some world, if you find yourself studying some physical system, and nobody tells you what the symmetries are. Nobody's handing you a Lagrangian. But if you happen to notice that there's a massless degree of freedom, or a nearly massless degree of freedom, then what you should try and do is work your way backwards and try and understand whether that massless degree of freedom is the Goldstone boson of some symmetry. And then once you have a symmetry, that's awesome. And indeed, as we'll get to, maybe by the end, as we'll get to, there's a very important piece of history in particle physics where that was precisely the case. Good. Other questions? Now, so far we have considered just a U1 symmetry, but it's easy to generalize the above analysis to sort of non-abelian symmetries. So let me just give you an example. Let's take the case where we have not one scalar field with a Z2 symmetry or two real scalar fields with a U1 symmetry. But let's take n scalar fields labeled by an index I. Okay. Here I'm using the summation convention, so the repeated indices are summed over. And let's make sure that all of the scalar fields have the same mass and the same quartic coupling, so that this theory has a rotation symmetry, not a spatial rotation, but an ON rotation, where under an infinitesimal ON symmetry, delta phi is given by, it'll be given by an ON generator matrix Tij times phi j. And a general ON symmetry will be described by some parameter theta that describes this symmetry. Now this is a global symmetry, so the thetas here are constant. And again, let's take the case where m squared is less than 0. Then the minimum energy solution will be given by solutions where, again, phi is equal to a constant. So now the n vectors phi I will be equal to some set of constants vi, where v is an n-component vector whose length squared, well, is given by that parameter m squared in lambda. Then what we want to do is imagine rewriting the theory where we expand around this vacuum what you will do is discover some number of massless bosons. That is to say, massless scalar fields. And the number of massless scalars is equal to the number of broken symmetries that is to say, the number of ON generators which act non-trivially on the phi I equals vi. So let me describe that to you a little bit more carefully. But maybe before I do that, I could even draw a picture. Okay. So let's consider the case where n is equal to 3. Okay. So our scalars have an SO3 symmetry. Then what is the space of solutions? The vacua, well, are points on a sphere. So if you think about phi space, so if you think about phi as three-dimensional space, then the vacua will be points on a sphere. And the idea is that any one vacuum is going to be some point on that sphere. And so the question is, of the SO3 symmetries, how many of them get broken once the vacuum is chosen to be that particular point on the sphere? Well, the number of broken symmetries is the number of SO3 generators that don't leave that point invariant. So in particular, you could imagine there's one SO3 generator which is given by, which gives you a rotation around that axis. So that leaves that point invariant. So that symmetry is not broken. So even if you went and you re-expanded your theory around that point, you would still have some, you would still have that U1 symmetry would be unbroken. Okay. So this U1 is unbroken. But all of the other SO3 symmetries will be broken. If you tried to do a rotation, say, around this axis or around the axis that points out of the board here, then those would both move this point around. Okay. So those symmetries will be broken. So the other two are broken. So in the present case, when you expand around this vacuum state, you will have two massless Goldstones. And more generally, if we have an ON symmetry, then you will have n minus 1 massless bosons. I mean, I guess the way that you could see this a little bit more concretely is you could imagine, say, taking Vi to be, if you want to write it out in vector form, the vector whose last component is non-zero. And then you would ask, well, of the various symmetries, as described by the n by n generator matrices, how many of them have have a final column? How many of them will give you a non-zero answer if you multiply them by that vector? Another way of saying that is that how many of them have the j component being non-zero when j is equal to n? And if you think about it, there's an n minus one dimensional space of these, because these are antisymmetric n by n matrices, and so the space of those where the last column is non-zero is n minus one dimensional. If that's not entirely clear, just stare at this picture. Okay. Hopefully that picture is a little bit more clear. The idea being that in the SO3 case, if you choose a point, then there's a U1 that leaves that invariant, and then there's two other generators that get broken. Yes?
Can some of those goldstone become degenerate? Like, for example, the lower the temperature, some of the quantum between the freeze out.
Well, they're massless, so...
So they don't freeze out. But if they pick up the mass, they could.
Well, I mean, okay, when you say degenerate, I don't know what you mean.
Well, the
Well, they're-
example would be if we pull down the quantum system, then some of the degrees of freedom freeze out and they cannot participate
Well,
anymore. So something
I mean,
like that.
first of all, if we talk about unbroken symmetries that are only spontaneously broken, they're exactly massless. And so they never, even at very low temperature, they're always still present. Obviously, if you break the symmetry, they'll acquire some mass. And then you could ask whether, like let's say that we broke the symmetry. Here's an example, Let's say we broke the symmetry by changing that sphere into an oval, okay? Then you could ask whether it's the same, whether it's like the same, I don't know what you call the analog of the radius of an oval. I forget what they're called, but whether the principal axes are the same in the two different directions. So if you made this an oval, if you made this slightly, like let's say this was the Earth instead of an actual sphere, the Earth is slightly squashed, okay? And then if you took your vacuum state to be the North Pole, then you wouldn't have an exact Goldstone boson, right? Because you don't have that exact spherical symmetry, but you would have very nearly massless fields. And those two fields would be degenerate because the Earth still has that rotational symmetry. Yeah, okay, but that's neither here nor there. Okay, yes. Any other questions? So of course one could check explicitly by expanding out the action that you would get these n-1 Goldstone bosons, but I think it's a reasonable, straightforward exercise that just mirrors the one that we presented earlier. Good. And then, so far I've talked almost entirely in terms of classical physics. But the point is that if the symmetry is not anomalous, the Goldstone bosons will remain massless, even in the quantum theory. Whereas if you have an anomaly and the symmetry is broken by quantum mechanical effects, then you could these Goldstone bosons could acquire mass. Good. Any questions? So what I wanted to describe now, and I hope we'll see if I have enough time for it. I might have enough time. I won't have enough time. What I wanted to describe now is probably the most famous case of a Goldstone boson in particle physics. And this will kind of also serve as a bit of an introduction to our discussion of the Standard Model. So in particular, I'd like to talk about the description of pions as Goldstone bosons. So, let me pause. So were there any questions on Goldstone bosons before I continue? So, what I want to start with is I want you to remember a fact that we discussed in our discussion of particles with spin 1/2. So what I want you to do is remember that a Dirac fermion has a special symmetry known as chiral symmetry when it's massless. So this is something that you probably reviewed last time when Guy talked about chiral anomalies. Did he talk a little bit about this? So how does this work? Well, let's see. Usually it reconnects itself. Okay, there we go. So if psi is some 4-component Dirac spinner, then your Lagrangian, so the general Dirac Lagrangian, is psi bar I d slash minus m psi. If m is equal to 0, then that is invariant under not just the charge rotation symmetry, where psi goes to e to the I alpha psi, but also under the chiral symmetry, where psi goes to e to the I alpha gamma 5 times psi. And indeed, when the mass is equal to 0, we often separate a Dirac fermion into its left-handed and right-handed parts. So I'll denote the left-handed part of a fermion as psi left, and it's given by 1 minus gamma 5 acting on psi, and psi right as 1 plus gamma 5 acting on psi. So gamma 5 is an operator that measures the handedness, so it's either plus or minus 1, plus 1 for a right-handed field, minus 1 for a left-handed field. And these combinations here are the projection operators onto the left or right-handed fields. So here I'm writing everything in terms of 4-component Dirac spinners, but we can also write things in terms of 2-component Weyl spinners. I don't know if Guy reviewed that. We discussed it last semester briefly. I don't know if Guy reviewed that last time. Did you review the Weyl spinners a little bit last time? We'll do it a little more because they're going to be important in discussing the standard model. But the basic idea, for our purposes, we don't really need Weyl fermions. In particular, what I want to do is I want to imagine that I'm considering the 2 species of lightest quark. Those are the up quark and the down quark. And compared to the mass scales that are relevant for QCD physics, these quarks are very, very light. And so they're so light that I'd like to approximate them as massless. So that the up mass and the down mass are approximately equal and both 0. In this case, the system has a very large symmetry. So the theory of 2 light quarks, which are 2 Dirac fermions, U and D, well, for the present purposes, they're Dirac fermions U and D, which are massless. then has a giant global symmetry. In particular, it has a U2 times U2 global symmetry. So what do I mean by that? Well, what I can do is, because the two particles are massless, I can imagine separating them into left-handed and right-handed components, and then I could take their left-handed components and multiply them by some unitary 2x2 matrix, or I could take their right-handed components and multiply them by some unitary 2x2 matrix. Now, if the up and down quark were both massive but had the same mass, then I could do the same thing, but U left would have to be equal to U right. I could take U and D and multiply it by a 2x2 unitary matrix times UD. But in the limit where I can regard these guys as massless, that symmetry actually gets doubled. And just as a bit of language, I'll just tell you that, well, okay, let me leave that aside for now. So we sometimes write this global symmetry as not as U2 times U2, but as SU2 times SU2 times U1 times U1. Using the fact that U2 is equal to SU2 times U1. There's the overall U1 phase factor, that's just the phase in the U2 matrix, and everything else is SU2. And we often use L and R to denote whether we're talking about the symmetry of the right-handed or left-handed guys. And frequently, we actually write it a slightly different way. We write it as SU2 vector times SU2 axial times U1 vector times U1 axial where V is left plus right and A is left minus right. In particular, what do I mean by that? A little bit more precisely, what I mean is that the SU2 V, or the U2 V, is given by the case where U left is equal to U right, and then the axial symmetries are generated by those where U left, say, could be equal to U right inverse. But a general transformation will have U left not equals to U right, but the SU2 subgroup of the vector, SU2 vector, or the U2 vector, is given by the ones where U left is equal to U right. Is that clear, more or less? Now, if you look at the particles that we know and love, the vector symmetries are obviously there. Okay? They're sort of clear. So what are the vector symmetries? So U1 vector, what does U1 vector do? Well, U1 vector is just the phase rotation of U and D, where you multiply them all by a phase. What is that? That just counts the amount of charge that there is. So U1 vector, if you wrote down the associated conserved charge, that just counts the number of units of charge. So the symmetry, so the global symmetry is a charge that counts the number of U's and D's minus the number of corresponding antiparticles. So the conserved quantity associated with U1V is just charge. Okay. Or if you want to say it a little fancier, it's quark number. Or in the language of particle physics, because we never actually observe free quarks, you only observe them in combinations, it actually leads to what's known as baryon number. baryon being a bound state of 3 quarks, such as a proton or a neutron. And similarly, we have an SU2 vector, which is the one where u left is equal to u right, is some non-trivial SU2 matrix. And this tells us, so this SU2 vector has a name. We call it isospin. I'm sure I gave you a problem set at some point earlier where you played around with isospin a little bit. And the basic idea is that this SU2 vector is a perfectly nice unbroken symmetry. And because of this isospin symmetry, bound states of quarks will organize into SU2 representations. So in particular, if we look at the particle content of the various nucleons, particles made up of quarks at low energy, well, you have a proton and a neutron. The mass of the proton and the neutron is very, very similar. Okay? That's reflecting the fact that they are in an SU2 doublet, an isospin doublet. In particular, they're in the two-dimensional representation of the SU2 vector. And they have a mass which is about a GeV. Okay. Likewise, there's a slightly less famous set of light particles known as the pions, and there are 3 of them, and they transform in the 3-dimensional representation of SU2. Okay. So they transform in the triplet representation. And they also have a mass, which is light by the standards of QCD or nuclear physics. In fact, it's about 1/10 that of the protons and neutrons. It's around 130 or 140 MeV. And if we wanted to, we could write these down explicitly in terms of their bound states of quarks. So a proton is an up, down, down. A proton is an up, up, down. A neutron is an up, down, down. Up quarks have charge 2/3. Down have charge -1/3. That's why a proton has charge 1, and a neutron has charge 0. And then these various pions are bound states of 2 quarks rather than 3 quarks. So, for example, the pi plus is an up-down bar, and pi minus is an up bar down, so an anti-up and a down, or maybe the other way around. I can never remember. And then a pi 0 is some other combination of ups and downs. But the real question is, why don't we also see particles in representations of SU2 axial or SU2 vector? So what about, U1 axial or SU2 axial? Well, U1 axial is easy. You learned last time that the U1 axial symmetry is anomalous. Did you learn that last time? More or less? Did you learn that last time? Okay, I have to find out exactly what Guy taught you last time. Did he teach you that?
I asked specifically about that, but it came at the end of Tuesday lesson.
Okay, good. So the U1 axial is anomalous. That is to say, it's broken by quantum mechanical effects. However, the SU2 axial is not broken. Rather, it is spontaneously broken. As was originally postulated by Nambu. Hence the name Nambu-Goldstone boson, instead of just Goldstone boson. So what is the basic idea? Remember, a symmetry is broken when the vacuum state is such that some operator has a non-trivial non-zero vacuum expectation value, and that operator transforms under the symmetry. So, for example, in the case of a massless, a U1 scalar field, the VEV of the scalar field was non-zero, and that VEV, rotates under the U1 symmetry, and so that U1 got broken and it turned into a Goldstone boson. The point is that in the ground state of QCD, this SU2 axial is spontaneously broken. So in order to sort of motivate this, I want you to sort of remember the intuitive picture that you might have in your head of a superconductor. So in a superconductor, what is the idea? The idea is that you have electrons but these electrons undergo some sort of strong interactions, not just Coulomb interactions, but some sort of strong interactions because they're screened and who the hell knows what else goes on inside a superconductor. And this makes them attract, and so they bind to form pairs. Okay. Now, electrons have spin 1/2, but they can bind together to form something with spin 0, so it can be a scalar field. But it's a charged scalar field, just like that field phi that we wrote down. And in a superconductor, the ground state forms pairs so that the expectation value of this 2-electron operator will be non-zero, and that's going to break the charge rotation symmetry. So the idea is that in the vacuum state of QCD, whatever the strong interactions of QCD are, the fact that we don't see this SU2 axial is pointing to the fact that quarks form some sort of bound states. Just like the Cooper pairs, in a superconductor. In particular, what do we mean? What we mean is that some quark bilinear has a vacuum expectation value that is non-zero. So let's start thinking about what kind of vacuum expectation values we could write down. Well, it has to be a scalar. And these quarks come in 3 species of color, so it has to be a color singlet. So let's start thinking about what sorts of things we could write down. So let's let Qi be the doublet. So let's let Q denote this doublet of an up and a down quark. Then if you want to write down something, first of all, it can't have charge, okay, because otherwise you would break electromagnetics. Otherwise, we would be living in a superconductor right now. Okay. Otherwise, empty space would be a superconductor. So you can't break charge, which means you need one for every, you need a Q bar Q kind of structure. So the simplest bilinear, and indeed the only one that you can write down that is consistent with Lorentz invariance, is Q bar Q, which if you write it out, so Q is equal to Q left plus Q right, because left is the projection onto the left-handed part, right is the projection onto the right-handed part. So if you expand this out, what is this? This is Q left bar Q right plus Q right bar Q left. And I'm using here the fact that Q left bar times Q left is equal to 0. That's the statement. Well, that's an easy enough statement to check because bar takes gamma 5 to minus gamma 5. That's another way of saying that you can't write down a mass term for a Wiener fermion. But in any case, this Q bar times Q, well, if you ask how this behaves under these various global symmetries, so under a general U left, and U right, how does Q transform? So Q left goes to U left times Q left, and Q right goes to U right times Q right. So Q left bar times Q right goes to Q left bar times U left dagger, U right times Q right. And similarly for Q right bar times Q left. And this is equal to Q left bar, Q right, only if U left is equal to U right. So the SU2 vector and U1 vector are preserved. They are unbroken. But if this quark bilinear has a vacuum expectation value that is non-zero, the SU2 axial is spontaneously broken. Okay, so that's a perfectly lovely story. Except there's one thing, if there's one thing that you've learned in this class, it's that whenever you have a spontaneously broken symmetry, you get a massless field. SU2, there's three SU2s. SU2 is a three-dimensional group, so you expect three massless fields. Oops, what just happened there? So let's go back and look at what the spectrum of particles look like. So we expect three massless fields, and lo and behold, we have three pions. And if you look at their mass, well, it's not massless, okay. But I started out by assuming that the up and down quarks were massless. They're not massless. They're light, but they're not massless. And so the pions, well, they're almost Goldstone bosons. They're the nearly massless Goldstone bosons of the spontaneously broken, not quite symmetry of the up and down quarks. So the pions are the Goldstone bosons. And I think it was this sort of realization of Nambu that was probably most responsible for his Nobel Prize of at least the last couple of years. I forget exactly when it was, the last couple of years. And I think this is a really beautiful illustration of the general principle that, you know, symmetries are not obvious. You know, if you are in a world with a broken symmetry, it's not obvious. But if you find a massless field, then the first thing that you should do is try and see if that massless field is associated with some broken symmetry. It works sort of famously well in condensed matter physics, and here's an example of it working famously well in particle physics. So sorry I went overtime for a few minutes. Maybe I should just stop here and see if there are any questions. Yes?
So what about neutrinos? Can they be?
Neutrinos are fermions, they're not scalars. So, you know, I mean, in theories, yeah, okay. There are theories, so there are ways that you can get Goldstone bosons with spin. The point being that the symmetry parameters that we talked about above were scalar symmetry parameters. So where did I write them down? Yeah. Let's go down here. So here these symmetry parameters were scalars. And so because of that, the associated Goldstone boson was a scalar. There are theories, I mean, there are kinds of symmetries where the symmetry parameters have spin. This is called supersymmetry. And there are associated Goldstone, they're not bosons anymore. So they're called Goldstinos, actually, is the name people give them. Because Eno means, okay, never mind. So, and they would have spin 1/2. And so, there certainly are, in theories of supersymmetry, that supersymmetry is spontaneously broken. There are Goldsteinos. I don't know, I assume that there's something bad will happen if you try and get the neutrinos as Goldsteinos. I'm pretty sure that's not going to work, but that's the kind of thing people think about. I mean, there are also theories like, the natural question is we have massless vector fields. Right? So are those Goldstone bosons of some broken symmetry? Not as far as we understand. I don't think there's any way of thinking of them that way, but it's something you could try. Well, okay, there might be a way that you could think about them that way in Kaluza-Klein theories, but let's not do that. Yes?
Can you compute the pion masses by treating the up and down quark masses of
Absolutely.
equation parameters?
This is a famous exercise. When I took quantum field theory, that was an exercise we had to do because the person I took quantum field theory discovered that formula. It's actually a lovely group theory exercise. It was a little hard for a problem set, but yeah, I mean, I don't even know who it was. Maybe it was, I think maybe Glashow and Coleman did it first. But yeah, absolutely. So, no, that's a great point. So you can now do a perturbation theory where you treat the quark masses as perturbation parameters. Actually, I think for SU2 it's pretty easy, actually. I think I think it might be a good problem. And you can actually understand exactly where the pion masses come from. It's a little, yeah. I mean, there's some subtleties there. One needs to be, when we write down, I mean, this is really something that maybe you talked about with Guy when you talked about QCD, but, when you talk about, it's sort of tempting to think about, so for example, I told you a pion mass, I told you that the pion was a bound state of 2 quarks. So it's like the pi plus is like an up bar and a down. And so it's very tempting to say, well, the pion mass is the mass of the up plus the mass of the down. But you couldn't be more wrong. Okay? And the reason you couldn't be more wrong is that that would be totally true if you were talking about a weakly coupled theory, weakly coupled quantum field theory. But at very low energies, QCD is strongly coupled. And so that most of the mass of these particles does not actually come from the masses of their constituents, but rather from the binding energy. So this is a famous problem, like on qualifying exams, to try and trick people. The famous qualifying exam problem is like, what's the mass of the proton if the up and down quarks have 0 mass? And the answer is, it's pretty much what it is if they have non-zero mass, because almost all of the mass of the proton comes from gluon binding energy. And it's some strongly coupled physics that is kind of hard to study perturbatively. But I guess it's lattice results where people compute the mass of the proton in a world where the quarks have 0 mass. Yeah, I mean, all of this business, I'm going to stop. I'm way over time. But, people talk about how the Higgs mechanism is responsible for all of the mass of the elementary particles. There's a sense in which that's bullshit. Because like the mass of the proton and the neutron comes primarily from the binding energy of gluons, from some strongly coupled dynamics. It's only things like the masses of the leptons and stuff like that that really comes from the Higgs.
So it's still responsible for all of the mass of all the elementary particles.
Yeah, no, I mean, it's the elementary, right. I mean, it depends on what you mean by elementary. Proton's not elementary because it's bound states of other things. So it's mostly, so for the masses of, but people who read newspaper articles don't know that. Okay. So I always get slightly annoyed when people say that, but I guess I understand why, because you have to sell newspapers. Okay, I'll see you on Thursday.